Science in the news and magnetic resonance imaging, or MRI. This is in the news from my point of view, following on from my video on ferrofluids, because ferrofluids are used as a contrast medium in MRI, and I thought, well, if I'm going to talk to people about ferrofluids as contrast medium, then maybe I should talk about MRI as well. Because if you've done or are doing GCSE, you'll have come across ultrasound as a medical imaging technique, you'll have come across X-rays, you'll have come across CT scans, which are 3D X-rays. You might even have heard of PET scans, but you haven't and won't come across MRI particularly. So this is worth knowing about. So what they do is they apply a really strong magnetic field to the body. This is completely harmless, which is one of the big attractions of MRI. Then they pass a radio frequency signal through the body. They produce a magnetic field and radio pulses coming from the body, and it's those that are used to form the image. And they're very detailed. So how does this work then? Well, most of the body is water. Water contains hydrogen, and hydrogen nuclei, at least hydrogen 1, are protons. And those protons spin and they produce a magnetic field. Now, you might say, how does that work? You should know, if you're at school or been at school for a while, that protons have a positive charge. And magnetic fields are produced by moving charge. So because the protons are spinning, they're moving, and because they're moving, they produce a magnetic field. So what you have here are little nuclear magnets. The physics here is called nuclear magnetic resonance, NMR, although the machines are called MRI, magnetic resonance imaging. So these spinning protons, because they have a magnetic field around them, will be affected by a magnetic field. And this is where the strong magnetic field comes in. So here's a cross-section through a scanner. You have the radio frequency coils to produce that radio frequency that we fire through the body. You have these magnets around the outside, making up much of the bulk of the machine, and you slide your patient in. This is a very small space, so it can be quite claustrophobic, and it's very noisy as well, and you have to lie very, very still. These gradient coils, I'm not going to talk about this very much. This is an overview of MRI rather than an in-detail view. If you're studying this at A-level, you'll need to know more, but this is an overview to give you a flavour of how these things work. So this magnet, this main magnet, is superconducting. Superconducting means it has no resistance, no electrical resistance, which is amazing. It does all kinds of incredible things if it has no electrical resistance. But to do that, it needs to be very, very cold. Now 4.2 Kelvin is about minus 269 degrees centigrade. This is seriously cold. But if you cool it to this sort of temperature, then it becomes superconducting and you can produce intense magnetic fields. Now, because of these very, very powerful magnetic fields, you have to have all electromagnetic fields, all metallic objects need to be away from the room. The room needs to be shielded, because if that thing is magnetic, if it's iron or steel, then it can become a projectile and potentially very, very dangerous. There are other effects if they're not made of iron or steel, but the room needs to be clear of any metallic objects and all other electromagnetic fields. So, the protons are spinning, they're pointing in random directions though. And when you apply this other magnetic field, those randomly spinning protons will align with it. They will either align parallel with it or in the opposite direction. So in parallel and in the same direction, like this one here, or parallel and in the opposite direction. Now you can imagine lining up like this is easier. It's a lower energy state than this one. This one's going to be unstable. So while they're spinning, they're also precessing, which is to say they're spinning, but it's a bit like a spinning top. The axis of rotation is spinning around like this, slightly at an angle. And so as it spins, it's turning, and this axis around which it is spinning is rotating. That is the precession. Now, if only one of these protons was precessing, very weak field. But if you hit them with this radio wave at just the right frequency, and again, I'm missing out some detail here, but if you hit the right frequency, then what you will do is to get them all to flip into that higher energy state and precess together in phase, which gives you resonance. Now, resonance is something that at GCSE you don't look at all, but resonance is something you're very familiar with. If you blow into the top of a milk bottle and you get that note, or any kind of bottle for that matter, and you get that note if you hit it just right, that's resonance. Resonance is how musical instruments work. Resonance is what you have when you have a badly balanced wheel on your car and you get that serious vibration in the steering wheel when you hit a particular speed. That's resonance. You're getting this maximum vibration at a particular frequency. That's what's happening here. And that resonance gives you a strong enough magnetic field to allow you to image. Now, when you remove that signal, those protons lose energy, they relax, and they do that in two ways. They flip back into the lower energy alignment, or they lose energy to other nuclei and go out of phase. Now, that relaxation time, the time it takes, is characteristic of the tissue. So now you can see how the computer can build up the image of what we're looking at, because that relaxation time is characteristic of the tissue you're looking at. So watery tissue has one relaxation time, fatty tissue has another, cancerous tissue is somewhere in between. And so knowing the relaxation times, you can know what you're looking at. The computer can plot what it's looking at. And the gradient field, well, this allows the operator to choose the bit of the body that they want to image. It allows them to do sort of a fly through of the body. They can vary the gradient field up the body, and they can image all the way from head to toe, a fly through of the body. And I'm not going to do much on this, but you have the field coils, the gradient field coils, in three different axes, the y-axis, the x-axis, and then the z-axis, which would come in and out of the page. So there you have it. So the computer can image using either the first relaxation time, T1, which is dropping out of that high energy state, or the T2, which is that giving up energy to other nuclei, or a combination of both. So here you have your summary. MRI scanners using really strong magnets, 1 to 2 Tesla. Now, to give you a feeling for that, your typical fridge magnet is maybe 1,000th of a Tesla. So this is 1 to 2,000 times stronger than a fridge magnet. The magnets used in some of the world's biggest science experiments are 10 times stronger than that. 10 times stronger than what we have here for the scanner. So they vary the field around the patient in 3D, and the gradient field is then used to fine-tune which bit of the body they're looking at. The resonant frequency then is varied, and you get images of the different parts of the body. So why bother? Well, for one thing, it's non-ionizing. There's no dangerous radiation involved, unlike X-rays, unlike gamma rays. CT scans are 3D X-rays. You don't have to go inside the patient at all. There's no surgery. There's no inserting of cameras down the throat to look into the stomach, for example. The patient feels nothing, although if you don't like enclosed spaces, it might not be a pleasant experience and it's quite noisy. There are no after effects, unlike treatment for cancer with gamma rays or chemotherapy, for example. Gamma rays, X-rays, CT scans are all ionizing radiation could cause cancer. You can image any part of the body in any direction you choose, and you can do that fly through, as I mentioned. You get this excellent soft tissue contrast. You're able to tell one layer from another really, really well. And of course, this is where your ferrofluid comes in. Why isn't it used all the time? Well, you can't look at bones so well. Really good for soft tissue, not so good for bones. Patients with pacemakers can't have MRI. Some professions are at higher risk from MRIs, welders, for example. And any metallic body, objects inside the body will be heated by the strong magnetic field. And that's a risk for metallic objects in the room as well. But if you have a joint replacement, then that's potentially problematic. And they're hugely expensive. Expensive to buy, expensive to set up, and you do have to be very careful when you're using them. Now, MRI comes in different forms. You have functional MRI, which allows you to image blood flow. Molecular MRI, you can look at biological processes going on. And magnetic resonance spectroscopy, looking at the distribution of certain chemicals in the body. So it's not just about taking pictures of organs. It does all these other things as well, tremendously useful to the medical profession. And this use of contrast agents, so this is where the ferrofluid came in. If you haven't watched my ferrofluid video, it's worth watching the videos at this point. But the contrast agent improves the resolution of the image. It changes the relaxation times to get you that brighter image.